Hello everyone and welcome to Control Engineering and Control Theory tutorials. In these tutorials we present real and applicable knowledge of control engineering, machine learning, signal processing, robotics, etc. In this video tutorial we explain how to easily solve the Lyapunov equation by using the Kronecker product. Furthermore, we provide a detailed explanation of Python code for solving the Lyapunov equation, and the Python code is given over here. Before I start with explanations, I need to emphasize the importance of the Lyapunov equation. The Lyapunov equation is arguably one of the most important and fundamental equations in control theory, control engineering, and signal processing. It's used for stability analysis of dynamical systems, it's used in control design, and it's also used in optimal control. This is because we can solve the Riccati equation by solving a series of Lyapunov equations, and the Riccati equation is necessary for computing the optimal controller. Consequently, if you're a student or even an engineer or even a scientist who want to master control engineering, you should definitely study the Lyapunov equation and you should learn how to solve this equation in Python, MATLAB, C or C++. Of course, since we live in the 21st century, people have written a number of functions for solving the Lyapunov equation. For example, in MATLAB we can use the function Lyap to solve this equation. Similar functions are written for Python or C and C++. However, if you want to really master control engineering or control theory, you should learn how the things work behind the scenes. That is, you should learn how to write your own solvers from scratch in Python, MATLAB, or C, C++. Only in that way you can obtain a long-lasting knowledge and deep understanding of control engineering and control theory. Also, before I start, I would like to mention that it took me a significant amount of time, energy, and planning to create this completely free video tutorial, as well as almost 300 video tutorials that you can find on my YouTube channel. And consequently, I kindly ask you to press the like and subscribe buttons. Thank you very much. Okay, let's start. Here is the Lyapunov equation. This matrix A is a known matrix, and often this matrix originates from a linear or a linearized system that has the standard form, A times X. The matrix Q is a constant and known matrix. Often it's assumed that this matrix is positive or negative definite. Here's the problem. Given the matrices A and Q, determine the matrix X, and that's our problem. Before I continue, I have to state a few important comments. In addition to this problem, people often state the following. Find the matrix X that's symmetric and positive definite. However, since this is just a starter video, that is, I'm not going to present the complete control theory in 30 minutes, I will not consider that case. The solution that's implemented in Python will miraculously determine positive definite and symmetric matrix X. So you don't need to worry about this additional condition. Let's see what's the main challenge in solving this equation. Obviously, this is a linear matrix equation. It's linear since our unknown matrix linearly enters this equation. However, the challenge is that this equation is not in the vector form. To illustrate this, people often parameterize the X matrix as x11, x12, x21, x22, and then they find this product that will depend on x11 until x22, then they add the result to this product that will again depend on x11 until x22, and on the other hand they have a matrix which is a quadratic matrix, let's say with the components q11, q12, q21, and q22, and once they do that, they obtain a system of 4 equations with 4 unknowns, where the unknowns are x11, x12, x21, and x22. You can definitely use this approach. However, this approach is very tedious and very prone to errors. Instead of using this tedious approach, in this video tutorial I will explain a very elegant approach for solving the Lyapunov equation. Namely, I will explain that by using the Kronecker product we can transform the Lyapunov equation into a system of standard linear equations that looks like this: s times x as a vector is equal to minus q, where S is a matrix that depends on our system matrix A, X is a vectorized matrix X. I will explain the vectorization operator later on, and Q is a vector obtained by vectorizing the matrix Q. And from this equation, we can simply determine X by, for example, inverting this matrix S. However, in practice, you shouldn't explicitly invert matrices. There are more sophisticated methods for solving linear systems that don't require matrix inversion, or that they implicitly invert matrices. However, for simplicity and for brevity, in my Python implementation, I will use this simple approach. To implement this approach, we first need to understand the Kronecker product. Let A and B be two arbitrary matrices. For simplicity, I will assume that these matrices are two-dimensional. This is my matrix A, and this is my matrix B. B12, B21, and B22. The Kronecker product between the matrix A and B is denoted like this: A cross with a circle B. And it's defined by, pay attention now, A11 scalarly multiplying B, A12 multiplying B, A21 multiplying B, A22 multiplying B. So what's happening over here? I take A11 and I multiply every element of the matrix B with A11, and I place the result over here. Similarly, I take A12, I multiply every element of the matrix B with A12, and I place the result over here. And I do that for the other entries, A21 and A22. And as the result, we obtain 4 by 4 matrix that looks like this. We have B11, B12, B21, B22, and here we have A11 multiplying, A11 multiplying, A11 multiplying, A11 multiplying. And here's how the complete matrix looks like. For example, this 2 by 2 block is obtained by taking the entries of B and by multiplying them by A21. Next, we need to explain the vectorization operator. Let us again consider the matrices A and B. The vectorized version of the matrix A is denoted by vec of A, and it's a column vector defined by taking the columns of the matrix A and stacking them on top of each other. For example, vec A is a vector with the entries A11, A21, that's the first column, then we have A12 and A22. How about vec B? Vec B is a vector obtained by stacking the columns of the matrix B column-wise. We take the first column, and here it is, B11, B21. Then we take the second column, and we have B12, B22. Next, let's explain a very important connection between the vectorization operator and the Kronecker product. That is, we want to relate the vectorization operator with the Kronecker product. For that purpose, let's consider the following equation. A times x times B is equal to C, where A, B, and C are arbitrary but known matrices. We want to solve this equation for x, where x is a matrix that we want to determine. It can be mathematically shown that vec of the left-hand side, that is the vec of A times x times B, is equal to B transpose Kronecker A times vec x. By using this identity and by applying this identity to this equation, we obtain B transpose Kronecker A multiplying vec x is equal to vec C. And this is a very important formula that we will use in order to solve the Lyapunov equation. Okay, here's the formula, and let's apply this formula to our Lyapunov equation. First of all, let's see what is vec of A transpose times x. We can write this formula as A transpose times x times identity matrix. Let's now compare what's written over here and what's written over here. Obviously, A transpose serves as the role of A, identity serves as the role of B, and consequently we have B transpose. That is, we need to take I and to transpose I, and I transpose is equal to I, and consequently we have I Kronecker A, and in our case, A is just A transpose. And let's see what do we have. We have multiplying vec x. Okay, how about this term over here? What is vec of x times A? Vec of x times A is vec of identity times x times A, and that's precisely equal to, let's apply the formula. Our A is now identity and our B is A. Let's see what do we have here. We have B transpose, that is, we need to take A transpose Kronecker Over here we have A, and A is identity matrix. Consequently, we need to write identity matrix over here. And we have vec x. Now, let's apply the vectorization operator to left and right hand sides of our Lyapunov equation. We have vec of A transpose x plus xa is equal to minus vec of q. Now, let's introduce the following notation. Vec q is simply staying as vec q. However, let's transform this expression. So what do we have over here? Vec operator is a linear operator, and we can write the result as follows. And consequently, let's apply this formula given over here. Over here, I erased the previous expressions and I wrote the last expression over here. Let's apply the previously derived formulas. Instead of vec A transpose times x, we can write identity Kronecker A transpose multiplying vec x plus A transpose Kronecker identity multiplying vec x is equal to minus vec q. Then we can write identity Kronecker A transpose plus A transpose Kronecker identity multiplying vec x is equal to minus vec q. Consequently, we have written our original Lyapunov equation that looks like this. A transpose x plus xa is equal to minus q in the standard form of linear equations. Here, this is a matrix, and we will denote this matrix by S. Consequently, we have S times vec x is equal to minus vec q. And from this equation, we can compute vec x as minus S inverse times vec q. Once we compute vec x, we can simply de-vectorize this vector to construct our original matrix X. Next, let's see how to implement this procedure in Python. First of all, I need to import the necessary libraries. I'm importing the NumPy library, and I'm importing over here the Python Control Systems Toolbox library as CT. Note, I created a series of tutorials on how to use the Python Control Systems library. I'm only using this library over here in order to construct the state space model. However, you don't need to use this library. You can simply use the matrix that I will construct. To repeat, I'm only using this library to find my A matrix such that I can have a stable system. You don't need to use this library. Okay, let's continue. Let's first learn how to compute the Kronecker product in Python. I construct over here two test matrices, A and B. Let's see these two test matrices. Here is A and here is B. The Kronecker product is implemented in this NumPy function cron. We specify the first matrix, we specify the second matrix, and let's see the result. Here it is. How can we verify this result? Well, this block over here is 1 times B matrix, and obviously that's correct. How about this block over here? It's 2 times B matrix. It's correct, and other blocks are correct. Next, let us see how to vectorize a matrix in Python. That is, this line implements the vec operator. Here's our A test, and let's try to vectorize this matrix. We call this method flatten on the A test, and this argument f means that we want to flatten column-wise, and finally we need to reshape the matrix as 4 by 1. Let's see the result. Here's our A test vectorized, and here's the A test. Perfect. Now let's see how to devectorize a matrix in Python. Here's our A test vectorized, and let's try to form A test again. To do that, we use the reshape function. We specify the dimensions of the matrix 2 by 2, and we specify that the order is column-wise. Let's see the result. Here is A test 1, and let's see our A test. Perfect. Perfect match. Now we know how to devectorize matrices in Python. Next, I want to construct my matrix A, and for that purpose, I will first construct a stable transfer function. I'm using this control systems library function zpk. I specify the zeros, the 0 will be at 1, and I specify the poles of my transfer function. And as the result, I obtain this transfer function. Next, I want to create a state space model out of the transfer function. Consequently, I'm calling this conversion function TEF to SS, and I'm printing out my state space model. Here's my state space model, and I will take this matrix A from this state space model, and I know that this matrix A is stable. Consequently, my Lyapunov equation will have a unique solution, and that solution X will be positive, definite, and symmetric. Okay, so let's extract our A matrix, and let's check the eigenvalues of our matrix A to make sure that the matrix A is actually stable. That is, that its all eigenvalues are strictly in the left half of the complex plane. Consequently, here's our matrix. Eigenvalues, they are -3, -2, and -1. The matrix is stable. Okay, next, let's create the right-hand side of our Lyapunov equation. Here is the right-hand side matrix Q. I deliberately constructed a matrix Q that's actually positive definite. Next, let's form our vectorized Q. That is, we're applying the vectorization operator to our Q, and here it is. Okay, next, let's form our matrix S. Here's our matrix S. We need to form this matrix. Let's do that. I will take the Kronecker product of identity and A transpose, and consequently, I obtain this part over here. Identity Kronecker A transpose, that is, here it is. Next, the second term is A transpose times identity and the Kronecker product. Consequently, it's the second term over here. And here's my matrix S obtained by simply summing these two terms. Okay, once I do that, I can compute my X vectorized. Here's my X vectorized. I need to invert the matrix S, and I need to multiply the result with vectorized Q. Let's do that. I'm calling this numpy function math multiply that performs matrix multiplication or matrix vector multiplication, since in our case Q is a vector, and I'm simply inverting the matrix S. I'm calling the function numpy linear algebra dot inverse, and here's our X vectorized. Let's see the result. Here it is. Okay, now let's devectorize our X vectorized in order to obtain the matrix X. Let's see the result. Voila! Here is our matrix X. Obviously, it's a symmetric matrix or almost symmetric since we don't see the numbers over here. Maybe they're not precisely, for example, this term might not be precisely equal to this term. However, up to numeric precision, this is definitely a symmetric matrix. So we don't need to worry about additional constraints on imposing that the matrix is symmetric. Okay, let's check the eigenvalues of this matrix, and we can see that the eigenvalues are actually positive, and this implies that our matrix X is actually positive definite, since we know that positive definite matrices have positive eigenvalues. Perfect. However, how can we verify that we have correctly implemented this procedure and that we have actually solved our Lyapunov equation? Well, we can compute the residual. So what is the residual? Let's go back to our sketch over here. Now, if we take this left-hand side, and if we add to this left-hand side plus q, the result should be 0. If x is actually the solution of the Lyapunov equation. So let's verify that. We will compute this part, and then we will add q to this part, and the result should be 0. So let's do that. Here's the left-hand side. Okay, let's see the left-hand side. Here it is. And let's add q to this left-hand side, and let's see the result. Voila, here's the result. We obtain a matrix that's very close to 0. This is because these numbers are 10 to the minus 15, 10 to the minus 16. That is, we are at the numerical precision baseline. Okay, that would be all for today. I hope that you like this video. If you like the videos I create, please press the like and subscribe buttons. Thank you very much.